I'm building an Arduino-based electronic setting circle, a kind of astro compass. Just aim it at the sky and it displays the direction it's facing, but in terms of right ascension and declination. Anyway, that's my project goal. But this video is about the TWI bus on the Arduino, the backbone that will integrate a few sensors, plus a display, some storage, and an encoder. I understand, I get it. An astro compass has limited appeal, not likely to be nominated for Project of the Month. This is the last you'll hear it mentioned in this video, but my application of the Arduino's TWI might be more interesting, so stick around. My plan is to operate the communications bus using the TWI subsystem of the Atmel 328, including interrupt-driven communication, something I've never seen demonstrated on YouTube. This is what you should stick around for. I'm developing on the Atmel 328P Explained Mini by Microchip. It's an Arduino Uno in all but name, and it has an onboard debugger. The final product, my final product, will be on either an Uno or a Nano, if it works out. It seems sensible to start the project by focusing on the TWI bus. But the bus can't stand alone. There can't be just a TWI bus. There needs to be something for the Arduino to talk to. I chose the OLED display because it's a write-only device, and so it's about as simple as it gets. We'll get complicated later. Right now, it's a good device to start TWI development with. This is old stuff, just for review. If you've seen any video or read any article about TWI, you know the two wires of the two-wire interface are SDA, carrying data, and SCL, carrying the clock signal. The Uno pins A4 and A5 are equivalent to SDA and SCL, respectively. Physically, the two-wire interface is built by bringing out the SDA and SCL lines from the Arduino. The wires are arranged in a bus topology. Devices connect to the bus by simply tapping into it. I've omitted pull-up resistors. The Uno is connected to only the OLED display over a short run of SDA and SCL. More than one Arduino can participate on the TWI bus and become master of it. However, in this project, there is only one candidate for master. Two additional wires supply 5-volt power and ground. The Atmel 328 has a TWI subsystem capable of autonomously performing bus operations. It can operate concurrently with the execution of the application program, and we'll demonstrate that shortly. There are 4 registers used to operate TWI as master. The address register isn't one of them. It's used to give the Uno an address when it behaves as a slave. In this project, the Arduino is exclusively master, and so it needs no address. Writing a value to the bitrate register sets the communication speed. Associated with the bitrate is a prescale value. It's set by writing to the only 2 writable bits in the status register. Both bits are initialized to 0, which sets the actual prescale value to 1, giving the standard range of the bitrate. I worked out reasonable settings for the bitrate register in this table. It's for a 16 MHz Uno, and the prescale is 1. With the prescale value equal to 1, writing 72 to the bitrate register sets up 100 kilobits per second. The master begins and ends a transaction. A transaction begins with a start condition and ends with a stop condition. Although this figure of a typical transmission is typical, it can have some variations. For instance, it might contain a stream of many data bytes. Curiously, a transaction might contain more than one start, but it can only have one stop, and the transaction ends there. The master sets the start condition to begin a transaction, and the control register is the key piece of the subsystem to set the start condition. There are 3 bits in the control register that together will cause a start condition to be set on the bus. Write a 1 to each of the enable, start, and interrupt bits. The enable bit essentially turns on the TWI subsystem. The start bit puts the start condition on the bus. It's counterintuitive, but writing a 1 to the interrupt bit will actually clear the interrupt flag. It's necessary to clear the flag to let the TWI begin an operation. Set the interrupt bit to clear the interrupt flag. The subsystem will not begin an operation unless the flag is clear. When the start condition is complete, the subsystem will set the interrupt flag to 1. The while statement tests for this and waits for it to happen. There's also a status register. It contains the status code that, in this case, indicates that the start condition has been transmitted. It's redundant, so I don't check the status register. Everything between and including start and stop is a transaction. After the master sets the start condition, it always writes the first byte of the transaction. The first byte contains the address of the correspondent device, plus an indicator as to whether the master will be writing to or reading from the addressed device. Traditional TWI addresses max out at 127, a number that can be expressed in 7 bits. So in an 8-bit byte, there's 1 bit left over. The inventors of I2C, the name TWI was born with, decided that the leftover bit would occupy the least significant position of the address byte. That bit has a meaning. If it's 0, it means there's more data, written by the master, immediately following this byte. Right now, we only have the Arduino master and the OLED slave, and the OLED is write-only. So transactions will always be addressed to the OLED, and the bit will always be 0. From here on, me and the datasheet are just going to call it the address byte. Just remember it also contains the read-write bit. The address byte needs to be pushed out onto the TWI bus. Fortunately, there's a register for that. In the sample source code, the OLED address is defined in the second line. The 7-bit device address and the read-write bit are converted to an 8-bit byte. That result is stored in the data register. To transmit the content of the data register requires that we assert 2 bits in the control register. As before, writing 1 to the enable bit enables the TWI subsystem. Writing 1 to the interrupt bit clears the flag in the control register and transmission begins. And when the interrupt flag signals it, the operation is complete. The address byte that we've just written is a special case of transaction data. It was the first byte following the start condition, and it means something to TWI. It's part of the TWI protocol, but it uses the same data register and control register setup as device data. And TWI rules require that each byte of data, regardless whether it's address data or device data, must have a 1-bit response. So referring back to that interrupt flag, when it indicates that the operation is complete, that includes the response from the device as well. A code in the status register will indicate that the address has been transmitted. It will also identify the response as ACK or NACK. In this trial, I didn't examine the status code. It's time to write some device data to the OLED. The OLED display needs to be configured and initialized with around 30 bytes of data. I'm not going to enumerate them right now, instead focusing on just getting those data bytes to the OLED over TWI. These bytes are device data, but each is transmitted, one at a time, in the same manner as the address byte. Data is loaded into TWDR, the data register, and as before, the enable bit and interrupt bit are set in TWCR, the control register. The OLED responds to each byte it receives. Each response is available as status in the status register. I don't test the status, just the TWINT flag. A stop condition ends a transaction. It's always the master that sets the stop condition. Setting a stop condition on the bus requires 3 bits to be written to the control register. The enable bit will enable the TWI module. The stop bit will set the stop condition. Writing 1 to the interrupt bit will clear the interrupt flag and start the bus operation. The stop condition is kind of an anomaly. Unlike the other bus operations, when the stop condition has been set, the hardware doesn't raise the interrupt flag like it did for, say, setting the start condition. There isn't even a status code for it in the status register. However, there is the TWSTO bit in the control register. We had set it to 1 when we issued the stop condition. When the condition has been set, the bit returns to 0. One final note. Neither the start nor the stop conditions elicit a response from a device. In other words, there is no ACK or NACK for start or stop conditions. I introduced the logic analyzer in the project introductory video. We're going to use it to see into the TWI bus. It connects to the bus like any other TWI device. The waveforms are displayed in pulse view, also introduced in the project introductory video. Pulse view conveniently interprets the individual protocol components as well as the data and acknowledgments in the transaction, and uses colors to identify the elements of the TWI protocol. Here are the first few bytes of transaction data. Time is represented on the horizontal axis and passes left to right. The top trace is showing the train of clock pulses, and the second is showing the data pulses that are interpreted as I2C data in the bottom trace. The transaction leads off with the start condition. The address with the right bit follows in the first byte. The bytes in the stream are all tightly packed, which is no surprise. The data was ready to go, and there was nothing else we had to do except pump it out. And the data flows until the transaction ends with the stop condition. In that stream, each byte was pushed onto the bus immediately following the byte before, with no delay, because it was sent as soon as TWI was ready. There was nothing going on that would slow down or interfere with the stream. But suppose there's work to do. Let's simulate that by inserting busy work in amongst the data byte transmissions. In real life, this could be data preparation for display on the OLED, or any work that the application was built to do. Each byte is shifted out onto the bus by storing it in the TWI data register and setting the enable and interrupt bits in the TWI control register. We'll squeeze in the busy work right here, just after launching the transmission of the data byte. When this bit of application work has finished, then we check the TWINT flag. If the flag hasn't recovered, we'll wait for it, but it shouldn't take long because some of the time was used up by the busy work. In some cases, the wait loop might expire immediately. Busy work, of course, is simulated by invoking a delay. Here the delay varies roughly around the time it takes to transmit a single data byte. Upon entry to the function, pin 5 is brought high, and it's released just prior to exit. So how does the TWI stream behave and interact with the application work? I'll show you. Here's pulse view with the addition of busy work. The top trace shows the TWI data stream. The second trace is the busy work. The busy work function raises one of the digital output pins upon entry and drops it just as it exits. That pin is monitored here. I finagled the busy work to vary, sometimes taking more or less than the transmission time of a single byte. Right here, for instance, the busy work takes less time than a single byte transmission. Upon return from the busy work function, the application has to wait the remaining time for the TWINT flag to pop before it cycles around the loop for the next iteration. Conversely, here, the busy work takes slightly longer than the byte transmission. The loop can't continue until the busy work returns, holding up the transmission of the next byte. But the payoff here is the overlap, long or short, between the data stream and the busy work. The busy work is concurrent with the data streaming over TWI. We haven't even started on interrupts, which we're going to do now. I contrived the busy work to roughly match the transmission rate with some variation. I did the busy work in chunks, and I coordinated them with the TWI. Mostly I kept the duration of a piece of busy work about the same as a transmission of a data byte. The thing is, that's difficult to manage outside of a demo like the one we just ran. The solution lies with the TWI interrupt flag. It happens that the TWINT flag can actually seize control of the program, interrupting its normal execution at exactly the right moment. The program suddenly finds itself executing code to service TWI precisely when it's needed. Coordination between TWI and the program doesn't need to be choreographed like I did in the demo. An interrupt is serviced by a specially defined function subroutine. The function has access to global variables, but can't accept arguments or return values because there is no calling statement. While executing arbitrary application code, the processor might find itself abducted, metaphorically speaking, and forced to execute this function, out of sequence, asynchronously, spontaneously, it would seem. By the way, this is not the function header, it's a macro. It builds a properly formed function header for an interrupt service routine. The argument passed to the macro makes this ISR specific to servicing TWI. Previously, we had to watch the TWI interrupt flag very closely in a while statement whenever we performed a TWI bus operation, to the exclusion of doing anything else. Now we have a function, an interrupt service routine, to intercept the TWI interrupt flag. We don't need these while statements any longer. Losing the while statement, however, means we lose context. Landing suddenly in the ISR, we don't know why we're here. The first and most important thing to do is to find out why we're here. I treated the status register rather rudely during the first half of this video. I ignored it at every TWI event. But now, with interrupts, it comes into its own. This figure shows the relationship between the data stream and the status codes available from the status register. Table 21-3 lists the same status codes plus the actions to take and how to take them, while in master transmitter mode. We've been in master transmitter mode all along. With only the OLED, that's all we can do. Transactions begin with a start condition, so let's send one, this time with interrupts. This statement is left over from earlier. Setting these bits in the control register caused a start condition to be set on the bus, and we used to watch closely the TWINT flag for notification when it was complete. But this time we add the TWI interrupt enable bit, TWIE. This bit will make the TWINT flag actually cause a system interrupt when the start has been transmitted. And the processor will get virtually hijacked to the interrupt routine to handle it. We don't have to wait for it. The table shows that when the start condition has been sent, the status code will be hex 08. That's our cue to send the address byte. To send the address byte, the byte itself is written to the data register, and in the control register, write 1 to the enable and interrupt bits, just like above. This time we also set the interrupt enable bit, so that when we've received a response to the address byte, we'll end up back in the ISR to handle it too. We don't need these lines here now. We've got them in the ISR. According to our new favorite table, as soon as we receive an ACK response to the address byte, we'll be back in the ISR to handle status code hex 18. We'll take the old code from the for loop, which pulls data from the OLED configuration array, but we'll add the interrupt enable bit to the TWI control register. An acknowledgement to a data byte has its own status code, but it's handled the same way as the acknowledgement to the address byte. Each time we receive an ACK for a data byte, we can send the next data byte. Earlier, we had a for loop to walk us through the OLED configuration array. Here, we manage an index, initializing it as we start a transaction and incrementing it with each data byte we send. Just watch out for the end of the data. When we've reached the end of the data, we stop. We've discussed that stop doesn't raise the TWInt flag when it's done, even though we've just cleared the flag, so there won't be an interrupt either. This is terminal. It's the end of the chain of interrupts, so don't set the interrupt enable bit in the control register. If we receive a NAC response for any reason, transmission is over. This applies to the address or data bytes. Send a stop. We shouldn't get a bus error, but we'll treat it like a NAC. This shouldn't happen either. It's a non-status status. This we'll ignore. There are just a few more changes to complete the conversion of this demo to interrupt-driven code. The array has an index now called IDX, and the busywork function has been removed. And setup sets the start condition on the bus, but no longer writes any other data. That's handled by the ISR. Don't forget to set the interrupt enable bit to make that happen. We're using the loop function now to implement a kind of superspeed version of blink. Blink is all alone in the loop function. There are no interleaving TWI status checks. We're not helping to push data out to the OLED. Here's the money shot. Blink is running too fast to see an LED blinking, so watch pin 5 in the second trace. Here we have a steady stream of data on the TWI bus, and simultaneous activity in the loop function, with negligible interference between them. And we didn't have to do anything to accommodate, manage, or synchronize them to each other, something we had to work at before bringing on the interrupt. Previously, too, the application had to set the start condition, send the device address, send each byte of the message, and set the stop condition, all while doing whatever it was built to do. Now the application doesn't have to get involved in each of those steps. It only has to start the process. It's time to get a little more daring. We also want to read data, and for that I'm adding the MPU 6050. I'm going to send it a reset command, and then have it send a few bytes of data for the Arduino to read. The device and the data is arbitrary, and I don't care what it is. I'm only interested in reading it successfully. We're focused on TWI, not the device. I changed the way the data buffer works. The data array now begins with its length and ends that many bytes later at a continuation byte. While stepping through a buffer during transmission and encountering the continuation byte, if it's 0, there's no more data. The ISR should send stop. A positive value indicates that there is more data, in effect another buffer, whose length is given by the continuation byte. The ISR should send a repeated start and carry on sending from this point. If the continuation byte has a high-order bit set, the master should switch to receive mode, send a repeated start, and prepare for incoming data, which will go into the consecutive buffer. For instance, the length of the OLED init array is 29. The 29th byte is 0, meaning there is no continuation. The buffer ends there. The MPU reset buffer has length 3. Counting from 0, the third byte is the continuation byte, and it contains 0, meaning there is no continuation. It's the end of the buffer. The MPU read buffer says it's 3 bytes long, but has a continuation length of 134. The high-order bit of the continuation byte being on indicates that the TWI mode will switch to master receive mode. Remove the high-order bit, and the residual value of 6 is the requested length of the incoming data. The trailing zeros will be overwritten by the incoming data. Speaking of the MPU, we'll define its address here alongside the OLED. I have 3 data arrays. If TWI is active, the buffer pointer will point to one of them. The device address variable will contain the converted 8-bit TWI address of the active device, including the read-write bit, and the IDX variable will index through the array elements in the active buffer to send or receive each byte. Setup will reset the MPU by setting the active device address and the address of the buffer containing the reset command. Then it will trigger the start condition on the bus. Using interrupts eliminates a lot of waiting for events, but while initializing, some things need to go sequentially, sometimes at intervals. The MPU needs some time for itself after a reset, but instead of hanging around, we'll use the time given us to send the OLED its initialization. Nonetheless, OLED initialization needs to wait for the TWI bus to become available. TWI is busy if the device address variable is not 0, or if the stop bit is still set in the TWI control register. I think it might be convenient to have a macro to test for the availability of TWI. In the loop function, we don't wait for anything. We waited in setup, but TWI could only send to one device at a time, and we had to initialize both devices before we could leave the function. Anyway, if the TWI bus is available, we'll use it to retrieve some data from the MPU. If not, as long as we're here, we'll blink the LED and leave. We know we'll be back to try the MPU later. The first entry into the interrupt service routine will be because we've set the start condition. We initialize the index to 1 so that when we eventually send a data byte, not now, it'll be the first one from the buffer, not the length. But we do send the address byte, and we keep the interrupt enable bit on in the control register. This same block of code applies to a repeated start. That'll happen when we run into a continuation byte. The second time we find ourselves here in the ISR will likely be because we've received an ACK to the device address. It's time to send the data byte we indexed when we were here during our previous visit to the ISR. This same code also applies to all the data bytes, so we'll check to see if there's available data in the buffer. If there is, we'll send it with interrupt enable so that we'll be back here to do it again. If we've run out of data, check the continuation byte. If it indicates a switch to receive mode, turn on the read bit in the device address and send a repeated start. Even if we're not switching to receive mode, if the continuation is greater than 0, send a repeated start. Otherwise, it's the same as these conditions. We're done. Clear the device address and send stop. If we send a device address with the read bit on and we receive an ACK, we're in receive mode. The first incoming byte is on its way, and we need to prepare now to return either ACK or NACK when it arrives. If the incoming byte is not the last, then set TWEA, enable acknowledge. When the byte arrives, ACK will be the reply. The byte will go into the buffer, and we'll set up to receive the next byte. If this will be the last incoming byte, leave TWEA alone. NACK will be the reply. When the byte arrives, it will go into the buffer too, but the stop condition will be set. I found an error. When the ISR sends a stop, it surrenders the TWI bus by setting the global device address to 0. The device address is checked when testing the bus availability in the main program. Therefore, the variable should have been declared volatile. Well, we've made it to the main event. The MPU gets the bus first for a reset transaction. That's the MPU address byte in pale green, including the write bit, with 2 data bytes, all surrounded by start and stop. Everything within is acknowledged. Then the start for the OLED address with the write bit. Notice that the blink pulses start almost at the same time as the OLED initialization, although the former is in the loop function while the latter is in the setup function. And there go the 28 bytes of OLED initialization, all with accompanying acknowledgements. We're in the loop function now, where if the bus is available, we send a preamble specifying register 3B for a length of 6 bytes. There's the repeated start and another address byte, but with a read bit. The data flow is now inbound to the Arduino for the 6 bytes requested. The Arduino responds ACK to all but the last. The transaction ends with stop. The Arduino goes on, requesting the same data over and over until power off. So that's it. I hope you're not too disappointed that we didn't get to Hello World. I set out to run a trial of TWI with interrupts. This is a basic example, but I think it proved viable and worth pursuing towards a practical application. I don't know what I'll do next. Hello World certainly ranks high among the possibilities. It'll depend a lot on the audience I earn with this video. I'll continue on with my project. I know I said I wouldn't mention it again, but hey, the video is over. Thank you for watching.